In this section, we're looking at one-sided limits. That is, we're trying to determine what the function value will be as x approaches a particular value. So let's look at this example for y is equal to f of x. This is example 1. And here we have a function that is piecewise defined over specific intervals, and we want to determine the limits as x approaches a particular value. So let's look at x approaches a first. So the limit as x approaches a from the left, so as x is approaching a, our function value is climbing up to 2. And as x approaches a from the right, our function value is also climbing up to 2. So we can say that the limit as x approaches a from the left is 2. The limit as x approaches a from the right is 2. And so therefore the full limit as x approaches a is equal to 2, because the limit from the right indeed equals the limit from the left. Let's look at the limit as x approaches b from the left. So we want to look at how we approach b from the left. So as x approaches b from the left, we can see that our function value is going down to 1. And as x approaches b from the right, we can see that we have to be on this part of the function up here, and our function is going down to 3. So the limit from the left does not equal the limit from the right. So therefore, the limit as x approaches b does not exist. Okay, so let's look at the limit as x approaches c from the left. So as x approaches c from the left, our function is going up to 4. And as x approaches c from the right, our function is going to 4. So therefore, the limit as x approaches c is equal to 4. Now, as we say, the limit, and this is the most important thing, the limit is the expectation. So as you notice in this here, even though the value at c is not defined, we can still talk about the limit, because my expectation is that if I could get as close as I possibly could, I would get to 4. So that's the limit. The limit as x approaches d, the limit as x approaches d from the left is 3. The limit as x approaches d from the right is also height 3. So therefore, the limit as x approaches d is 3. Okay, let's go on to example 2. So in example 2, we are given the function values at -1 and 1, because our function is defined to be x squared minus x minus 2 over x squared minus 1 when x is not equal to -1 and 1. So although we have function values, we're not going to be concerned about function values because we're looking at the limit. Again, the limit is the expectation. So we're looking at numbers that are close to 1, not necessarily equal to 1. So we're going to look at values of the function close to x equal to plus and minus 1, but not necessarily at those values. So looking at those that are close. So when we look at the limit as x approaches -1 and the limit as x approaches 1, we want to look at the fact that our function if we did direct substitution and we actually were to plug it into that function value, we would get something that might necessarily be a number, or we might get 0 over 0. So what we're going to do is we're going to factor this first. So this factors into x minus 2 times x plus 1 divided by x minus 1 times x plus 1. And as we can see, we can algebraically divide out the x plus 1s. And this function, when x is not equal to minus 1 and 1, is just x minus 2 over x minus 1. So now we want to do limit by direct substitution. And when I substitute minus 1 into this function, I get the limit as x approaches minus 1, x minus 2 divided by x minus 1. And that's minus 1 minus 2 divided by minus 1 minus 1. And this is 3/2. We look at the limit as x approaches at positive 1, we get the limit as x approaches 1 of x minus 2 over x minus 1. And this is going to give me 1 minus 2 divided by 1 minus 1, which is negative 1 over 0. And negative 1 over 0 is undefined. So this is an undefined value. So therefore, we're going to say this limit does not exist. Other limits by direct substitution, we want to look at the limit as x approaches 2 from the right. So we're just going to directly substitute 2 into our function value. And when we do that, we get 2 plus 1 divided by 2 minus 1. And that's multiplied by 2 squared plus 2, which is going to give us 3 times 6, which is 18. Now let's look at something that's a little bit more difficult. That is the limit as x approaches minus 1 of x squared minus 1 over x minus 1 in absolute value. So if we do direct substitution here, when we put in our values, we end up getting 0 divided by 0. And we know that 0 by 0 is an indeterminate form. It is different than 1 minus 1 over 0, which is undefined. This form is indeterminate. That means we don't actually know what 0 over 0 is. So we need to look at what the absolute value function is. So the absolute value of x is equal to the opposite of x if x is less than 0, and it's equal to x if x is greater than 0. So now let's look at the absolute value of x minus 1. And this is going to equal the opposite of x minus 1 if x minus 1 is less than 0. And it's going to equal x minus 1 if x minus 1 is greater than or equal to 0. So now we are putting in numbers that are a little bit smaller than 1, because we're looking at the limit as x approaches 1 from the left. So numbers that are a little bit smaller than 1, when we put them into here, what happens? Well, if the number is a little bit smaller than 1 because it's to the left of 1, then that means x minus 1 is negative. So if x minus 1 is negative, we need to use this definition for the absolute value. So now we will get that x squared minus 1 divided by the absolute value of x minus 1. Since we're looking at numbers that are smaller than 1, this becomes the limit as x approaches 1 from the left. of, well, let's write this as x minus 1 times x plus 1. And then, because x minus 1 is less than 0, the definition of the absolute value will be in this form. So we're going to get the opposite of x minus 1. So that gives us the limit as x approaches 1 from the left. And as you can see, I can algebraically divide out x minus 1 with x minus 1. So this now just gives me the opposite, or negative, x plus 1. So therefore, the limit as x approaches 1 from the left of this function is the same as the limit as x approaches 1 from the left of negative x plus 1. Direct substitution gives us minus 1 plus 1. So we get negative 2. All right, let's look at some trigonometric limits. We want to first take into account the fact that we know that the limit as x approaches 0 of the sine of x over x is equal to 1, and the limit as x approaches 0 of 1 minus cosine of x over x is equal to 0. So we want to use those in our limit. So the first problem we have is the limit as x approaches 0 of sine of 5x over x. And as you note here, when I look at this, I see the sine of x over x. And these two quantities are approaching 0 at the same rate. So what I have here is I have the sine of 5x, but I have x, and they are not approaching 0 at the same rate. So I need to modify what my function looks like. So I can write this as the limit as x approaches 0 of the sine of 5x divided by x, and I can multiply by 5, so I can put the 5 here in the denominator, and I can put 5 in the numerator. So essentially I've multiplied by 1. So this is the limit as x approaches 0 of 5 times the sine of 5x divided by 5x. And so that becomes 5 times the limit as x approaches 0 of the sine of 5x divided by 5x. So that is 5 times 1. So that answer is 5. The limit as x approaches 0 of the tangent of x over x. Well, this is the limit as x approaches 0. I can write this as the tangent, well, 1 over x times the tangent of x. So now that becomes the limit as x approaches 0 of 1 over x, and the tangent of x is the sine of x divided by the cosine of x. So I'm going to rewrite that as the limit as x approaches 0. I'm going to put the sine of x over top of the x, and then I'm going to have 1 over the cosine of x. And now I can see that this limit is 1, and this limit is 1. So therefore my answer is 1 times 1, or 1. Last problem. I have the limit as x approaches 0 of x minus x cosine x over sine squared of 3x. So we want to rewrite this as the limit as x approaches 0. I want to factor out that x. So now I can get 1 minus the cosine of x. And then I'm going to write the denominator as the sine of 3x quantity squared. So this is the limit as x approaches 0 I have x. Then I'm going to have 1 minus the cosine of x. And I have the sine of 3x squared. So if I take and put in the denominator here, the sine of 3x quantity squared, then what I need in the numerator is 3x quantity squared. So I can rewrite this. Oh, I forgot to put my 3x quantity squared in the denominator. So let's do that first. Okay. So now we get the limit as x approaches 0. 1 over 3x squared. Let's pull out the 1 over 9. Then I'm going to have 1x is going to be divided by that x. We can see they're going to divide out. We're going to get 1 minus the cosine of x. It's divided by x. So I see where here's my 3x squared right there. And then I'm going to have 3x over the sine of 3x quantity squared. Now let's take into account here that the limit as x approaches 0 of the sine of 3x over x, 3x is 1, and the limit as x approaches 0 of the sine, so let's go back. Let's look at the inverse of this. So 3x divided by the sine of 3x. This limit's going to be 1 over 1, which is again 1. And then if I square that, that's going to be 1. So now this is 1 over 9. These divide out algebraically. This limit is 0, and this limit is 1 squared. So now I'm going to get 1 over 9 times 0 times 1. So this answer is 0.